Indian Institute of Technology, Guwahati in 2011, specializing in RF and microwave engineering. He holds ME in Applied Electronics from Satyabama Institute of Science and Technology in 2005 and BE in Electronics and Communication Engineering from Bharatidasan University in 2001. Dr. Karthikeyan's research spans a broad range of areas, including additive manufacturing of RF circuits and antennas, fluidically reconfigurable devices, RF energy harvesting and wireless power transfer, SAW based circuits and antennas, frequency selective surfaces. He has successfully led multiple research projects funded by premier agencies such as DST, SCRB, ISRO, and Imprint 2, with grants exceeding rupees 2 crores. His ongoing project focuses on fluidically reconfigurable devices for future millimeter wave 6G applications using 3D printing technologies. Dr. Karthikeyan has supervised 11 PhD scholars, many of whom now hold prestigious academic and research positions globally. He has authored over 70 journal publications, presented at 45 conferences, and contributed book chapters in leading international volumes published by Springer. In addition to his research, he actively contributes to the academic community through organizing workshops and international conferences. He has served in key roles such as coordinator, publication secretary, and co convenor in various national and international academic events in NIT Trichy. His administrative contributions, including serving as the ISRO STIC coordinator and as a member of the Institute Purchase Steering Committee at NIT Trichy. With his deep expertise and active engagement in advanced research and teaching, Dr. S. Karthikeyan continues to be valued resource person for this FDP. Welcome, sir.
Yeah, thank you, ma'am.
Thank you,
So
sir.
thank you for the introduction. I thank the organizer for choosing me as a resource person for this workshop. So I hope so. Today, world is actually relying on interdisciplinary. So a communication engineer cannot only work on communication experts. Similarly, the knowledge of electronics and electrical also required for a mechanical engineer. So we are living in this world. So the tomorrow will be us only if we started accepting the interdisciplinary related research work. So by keep it in mind, actually we started that research on additive manufacturing about 8 years ago. We have executed a couple of projects also. So in today's topic, I will be discussing about the basics of additive manufacturing, not much mechanical oriented. In addition to that, the first part, I will be explaining what is additive manufacturing, what are its advantages, disadvantages compared to subtractive manufacturing, how it differs. Those points will be addressed. Then later on, I will be presenting the work what we have done in our laboratory, especially focus on the 3D printing of energy harvesting circuit for IoT based application. So this is the way actually I planned my talk. Let me share the presentation. I hope we will be able to.
Yes. Yes, sir, it's visible, sir.
So today's talk mainly focusing on additive manufacturing of antennas and RF components. Not only antenna we can fabricate, other than antenna we can fabricate many other components also. So based on the time, probably we can discuss about the talk one by one. So let's start with the introduction. What is additive manufacturing? So, by definition, additive manufacturing, shortly called as AM, refers to a process by which we are building up a component in layers by depositing a material one above the other. Very simply, by making a sandwich, how we are making each and every layer of sandwich one by one, like that, a product will be fabricated by adding one layer above the one. Finally, the product will be ready. So actually, this additive manufacturing, uh, there are many definition. Some people call it as 3D printing. Some people call it as rapid prototyping. All those three terms are actually same or not. Okay. So this additive manufacturing is actually not a new one. It is about 30 years old. But recently, the 3D printing is a famous word. It has been well documented and defined during the past couple of years. We are frequently asked, about my students as well as many people, what is the difference between the additive manufacturing, 3D printing, and rapid prototyping. Between the terms, the 3D printing and additive manufacturing, actually there is no difference. 3D printing and additive manufacturing are synonyms for the same process. Both terms refers the process of building parts by joining material layer by layer from a CAD file, computer aided design file, normally used in mechanical point of view. Opposed to the traditional manufacturing process, for example, like CNC based machining, where a part is built by subtracting material from block of material. 3D printing and additive manufacturing can be used regardless if the parts are fabricated either in plastic, metal, or rubber. They are building the product by layer. Based on our general perception, it seems as though who work in an industrial or manufacturing setting prefer additive manufacturing since it sounds more formal. But being a hobbyist, maybe we can prefer the term 3D printing. The 3D printing has been used moreover since inexpensive desktop printers became more popular. Nowadays, with a few thousand rupees, we can able to build a desktop based 3D printing machine. So that's why the hobbyists prefer the 3D printing, but industry people used to call it as additive manufacturing. The term rapid manufacturing is actually different from the 3D printing or additive manufacturing. Rapid prototyping, it is a technique for fabrication of a prototype model from a CAD file. In other words, the 3D printing is the process and it will make the final result. For example, rapid prototyping, we can go for making a small model of a product readily. Suppose if we want to build any big equipment, say for example, if we want to go for a 3D printed IC engine, okay. So before going for that, we have to make a small prototype using the rapid prototyping method. Once it is successful, we are satisfied about the designs, aesthetics, looking, then probably we can go for the actual manufacturing of the IC machine it, with the help of the additive manufacturing. Hope you understand the difference between the additive manufacturing and the 3D printing. So the conventional manufacturing techniques are subtractive type. As I told you already, we are going to build any object or equipment or a product from a material. Okay. So this material, with the help of the CNC machining and tooling technique, we are going to remove the unwanted parts from the material, and finally we will be having our the original project. It is very simple. That is how the statues are made from the rock. Okay, so raw rock, by removing the extra material, finally we will be going to get a good structure. Okay, but opposite to the subtractive manufacturing, when you look at the additive manufacturing process, we are having a material. Okay, the material may be of anything, any material. It may be a plastic or polymer or even metal, whatever it is. By introducing the process on this material, additive manufacturing process, actually the object will be generated. But the major difference here is the waste material will be less compared to the subtractive manufacturing. So this is the major difference between subtractive manufacturing and additive manufacturing. So additive manufacturing is an example of making a dosa. Okay, just for whatever the shape we wanted, accordingly we can make that shape on a dosa tawa. We will get the final dosa, or in technically we can call it as an object. But subtractive manufacturing, it won't be like that. We have to remove it a extra part. So technically, what is the major difference between additive and subtractive manufacturing? Subtractive manufacturing, we can use all the materials like plastic, metals, composites, ceramic, whatever it is. Similarly, the similar type of materials are available for additive manufacturing also. The material conductivity wise, actually subtractive manufacturing, it is very high because we will be using pure metals. But the conductivity wise, the additive manufacturing materials may be lower, suppose if it is made of the non-conductive material. The cost will be additive manufacturing low, but initial setup cost will be high because obviously waste is less. So we can come to the conclusion like the additive manufacturing cost is low, but it need not be the same for the for everything. Suppose if we want to go for a bulk production, probably the additive manufacturing cost will be very small. But on the other hand, subtracting manufacturing, once we install the setup, say for example CNC machine, it will high. Design flexibility, in the case of subtractive manufacturing, we have a less design flexibility, but here we can make a product the way which shape we want it. That way we can do it. Even the complex structure can be easily made with the help of the additive manufacturing rather than the subtractive one. So a lot of freedoms are there for the designer, fabricator if they go for an additive manufacturing. The mechanical strength will be lower. It depends on the geometry and material used. It need not be always lower. It may be higher also, depends on the material, but the mechanical strength will be high in the case of subtractive. The resolution will be actually very high in the case of subtractive manufacturing. High resolution. We can go for plus or minus 2.5 micron, but in the case of additive manufacturing, it will be around 10 to 50 micron. This also very depends on the what type of additive manufacturing technology we are going to deal. The material efficiency, as I told you already, additive manufacturing less material waste, but in subtractive manufacturing, it will be very high cost. Post processing, in the case of additive manufacturing, actually we need to do some post processing material, for example, curing, etching, removal. That means etching, removal means not the whole part, some of the unwanted part. Okay, so that thing will not be there in the case of subtractive manufacturing. When you coming to the application, you can use this additive manufacturing in many application. It is endless. They can use this additive manufacturing technology for manufacturing of the customized sports product, customized toys. Even we can make a customized furniture, customized textile, customized implants. For example, like artificial tooth, we can make it customized jewelry, aerospace, satellites communication, military equipment, the modern electronics, everywhere actually we can use the application of additive manufacturing is endless. I would like to highlight one or two important advantages. As I told you already, it is very lightweight. for example, if we want to make the buckle, we have everyone had experience of flying in aircraft, right? So the seat belt, right? We have to wear the seat belt at the time of, even in the car also, but mostly this example will give you an idea. It is more related to the weight, so that we can take the example of aircraft rather than the car seat belt. Okay, so the buckle will be there. The buckle will be normally made of metal, right? A conventional steel buckle weight will be around 150 grams. And so for the aircraft, actually we have to reduce the weight as much as possible. Okay, so the people will be looking for uh, uh, whatever the material, wherever they are going to use it, they try to reduce the weight. At the same time, the strength will be more. Okay, so they will be looking for that. So in order to reduce the cost as well as weight, so either they can go for the additive manufacturing or subtractive manufacturing. For example, that buckle is normally made of subtractive manufacturing. It will be very high. Suppose the same thing we can manufacture with the help of a titanium, and also you can very well see that there are some open spaces will be there in the buckle made of the additive manufacturing concept. So what will happen is, obviously there will be a less material, so the size reduction will be more. So the size will be approximately 50% smaller or 50% lesser than the original buckle. So the Airbus actually uses this kind of seat belt for its aircraft. So roughly the total aircraft weight will be reduced to 72.5 kilogram if they are using this additively manufactured buckle than the conventionally manufactured buckle. And not only that, it will save the cost also. If the weight of the aircraft it is less, then obviously the fuel consumption of the aircraft also very less. So like that, there are many advantages compared to the subtractive manufacturing if we go for additive manufacturing. The another one is, already I told you, the dental grounds, right? Though additive, with the help of additive manufacturing, olden days, suppose if you want to make a crown for the dentist, the normal technician will make only around 30 to 40 crowns per day. Suppose if you nowadays, you no need to just take the measurement with the help of the conventional thing. They have some plaster of Paris kind of thing. Those the mold of your teeth will be taken by inserting that solid material onto your into your mouth, and your the tooth impression will be printed on that. Then after that, the technician will be making taking that impression out of your mouth, and he will be making the tooth with the help of the material, okay, manually. But instead of that, nowadays, just like how we are doing the scanning, the same similar kind of pen type of scanning material is there. So with the help of that, they will scan your entire mouth, the teeth orientation, size, everything. So that scanned file will be actually given to the printer, 3D printer. So the 3D printer will print the teeth according to your measurement. Okay, so it will be very easy, very time consuming one. So the tooth implant is made after the scanning, so there is a chance of accuracy, high accuracy compared to the manually made tooth implants. So this is the advantages. The cost also will be very much reduced, and very quickly, within 1 day or 2 days, they will be able to make your implant rather than taking 1 week or 10 days in olden case where they are using the subtractive manufacturing. Similarly, suppose if any person met an accident, our skull is very, very important. If our skull uh, got broken in the accident, actually that has to be repaired. So each and everyone's skull is of very, very customized one. We cannot go for a that artificial skull material with the help of a uh, conventional material. So again, with the help of a scanning, they can make the a part of the skull with the help of 3D printing, and it will perfectly fit into the person's skull. So these are all some of the examples we can see. Who knows? Probably in future, maybe we can have a homemade, very small 3D printer that 3D printer even will make a 3D printed food. Even in some of the YouTube studio, I have seen so 3D printed cake. So immediately, just once you just key in the design, the cake will be actually built with the help of the food printer. Okay, 3D printer will print the food also. So nowadays, I have seen one or two YouTube video also. You can also check, you can get it right. So similarly, suppose I want to make a very customized brush with some what is the bristle hardness, whether it is soft, hard, or in between soft and hard, like that everything. What is the color? What is the angle? What is the handle style, shape? Everything probably I can customize this. So with the help of the scanner, I can scan it and then I will just give an input to that homemade 3D printer. The 3D printer probably will give you a 3D printer brush. Not only brush, whatever you want, we can make it. So probably in future, we don't know. Nobody, no need to go to any shop to buy a um, toothbrush or pen or many household item, whatever even the kitchen items, we can just have it in our own design instead of going to buy it in a uh, the standard vessel shop. Not only that, even jewelry also we can print it, anything. So we don't know. So the 3D, as I told you, the 3D printing is not a very new one. In 1980 itself, the additive manufacturing era started. The first additive manufacturing actually stereolithographic method. After that, laminated object manufacturing, selective laser sintering, fused deposition modeling, or material. Many things are there. During 90s, the earlier the 3D printing they only used for the non-conductive material, but nowadays the people are using for metal also. Metallic additive manufacturing technology like selective laser sintering, digital metal laser sintering, SLM, EBM, DMD, and so on. Many type of additive manufacturing technologies are at present available. So we can broadly actually classify the additive manufacturing into a different part. The AIM technology was initially discussed in 1980s by a scientist called Hideo Godam when he introduced polymer material to light and designed a three-dimensional prototype layer by layer. Later in 1986, Charles Hull invented a first AM technique, stereolithography (SLA), regarded as the first technology for fast prototyping and our first commercially available SLA AM technology. After Hull's invention, selective laser sintering (SLS) was developed by Carlos Descartes in 1988 that was using laser to melt tiny particles of a ceramic, plastic, or metallic to create a required objects. After a year later, the founder of Statasys, the famous 3D printer manufacturer, Scott Crumb, invented another popular EM technology called fused deposition modeling (FDM). Now, as per American Society for Testing and Material Standard F2792, AM is divided into 7 categories based on methodology or process of formation of the product, as shown in figure. The material jetting, polyjetting will comes under the material jetting, VAT photo polymerization, stereolithography, DPP, CDLP, and DLP will comes under this. Binder jetting, then material extrusion, FDM, LDM, or fused filament fabrication. All those things comes under this category. Direct energy deposition, sheet lamination, and powder bed fusion. Also, another three different category. Each and every category there are sub classification also there based on the material used, technology used. Let's start with the uh, stereolithography. So as I told you already, SLA is the most widely used rapid prototyping technology. It will produce a very highly accurate and precision based part. It was invented by a scientist called Charles Hull. in this and so-called material. So SLA, it is the first invented AM process. It falls under the vat polymerization technique, in which a liquid vat of photocurable resin is exposed to a UV laser. Sorry. A liquid vat of photocurable resin is exposed to a UV laser to solidify the layer, ultimately constructing the solid structure. It involves post-processing steps also, following washing to clean extra resin, UV curing, extracting supporting structure after printing, and lastly, metallized processes carried out. All these steps make manufacturing process time consuming as compared to the other manufacturing technology. It produces optimal miniature component as it has a very high resolution of about 20 micrometer and a surface finish of around 1 micrometer. So we can say that the stereolithography will provide us a very smooth surface compared to the rough surface in the case of FDM. Like FDM, this SLA also supports various polymers and ceramic materials. Ceramic SLA is widely used technology in printing, dielectric antennas, dielectric resonators, and other high frequency ceramics with the low dielectric and energy dissipation losses. The tolerance also the very good. Part size may be varying. It vary from 59 inches to 29 inches cross 19.710. So this is that standard one, but based on the bed size, this size will be either more or less, depends on the manufacturer. So with the help of laser, actually melted, and it will build the one other. Next, coming to the polyjet technology. The polyjet printing falls under material jetting. It is an example of inkjet technology that utilizes polymer to model 3D structure. As we have seen in the figure, it has two inkjet openings, one for structure design and another for building support structure. The jetting nozzle spray photoresin across X and Y plane layer by layer, following the CAD design coming from the computer. Design sample contains lattice periodic structure, which is linked or photopolymerized using a ultraviolet lamp. The support structure is water soluble, so it can be easily detached using the hand from the solution bath once the printing is completed. So it has the ability of fast manufacturing, smooth structure with a complex design. However, if further metallization is required, that process we need to add it if we want to make an antenna or any RF component with conductive property. The two inkjet nozzle also helps to print multi-material or multicolor by extruding different polymers simultaneously. If we want, we can use the multicolor also. Similarly, by using a different substrate material, we can fabricate an antenna with two different substrate having different dielectric concept. Say, for example, with the help of multi-layer devices, uh, this will be very much useful for creating a substrate with a different permittivity. Next, coming to the fused deposition modeling, it was developed by a strategist. In this process is Done. FDM uses material extrusion technique in which filament is melted inside liquefier chamber using an extrusion channel and positioned on layer in building platform. That layers ultimately result in construction of a desired object as shown in the figure. The nozzle diameter used in FDM is having the precision varying from about 100 to 200 micrometer, and printing phase of the device is little bit slow. For the FDM method, a large variety of thermoplastic materials are available. The materials commonly used in FDM based printing is PLA, polyacetic acid, or ABS, polycarbonate. Apart from this, we can use PEEK or Ultra material also. They will provide an outstanding electrical properties, strength and stiffness along with high durability. So this FDM method is very much useful for fabricating the dielectric part of the any RF system, and also it is very much helpful for making a conductive part of the RF system also. So conductive part will be made with the help of a material peak and ULTEM ultem. The substrate part will be made of either PLA or ABS. Next, coming to the SLS, selective laser sintering. The selective laser sintering was developed at the University of Texas in Austin by Carl Deckard and his colleagues. The technology was patented in 1989 and was originally sold by a DTM Corporation. The DTM Corporation was acquired by a 3D System in 2001. The powder used in this SLS is normally polymer. We have SLM as well as DMLS technologies. Both falls under the laser powder bed fusion technique (LPBF), in which powdered material, for example, polymer, metal, or ceramic, are used to design a part of an object. LPBF has the advantage of producing direct metal structure without undergoing any post processing or metallization process, overcoming the challenges such as brittle, low thermal conductivity, and high coefficient of thermal expansion faced by polymer resins in SLA, which makes component less efficient for high power RF system, but it is very much suitable for the low power RF systems. This will also will good size, thickness of tolerance, and speed is very high compared to the other systems. So other than that, many other techniques also there. For example, one of the famous printing technique is aerosol jet printing. It is very costly, and it can produce a track width of very even less than 10 micrometer width. So they are very much useful for very high frequency application, and VLSI making of a VLSI based interconnect. Those aerosol jetting based 3D printing is very much useful. So there are around 5 to 6 general manufacturing steps involved in additive manufacturing. If you want to make any object, whatever the object you want to make it, first you have to make a computer aided design model, CAD model. So using a standardly available CAD software, SolidWorks or any other AutoCAD, anything, whatever the software you are familiar, uh, then those software you can use to build up a model, CAD model of a object you want to print it or the object you want to manufacture it. Then that CAD model will be converted into a STL file, stereolithography file. So as I told you already, STL stereolithography is the very first RD manufacturing technique. So that format for giving a layer by layer information, whatever may be the manufacturing process, whether it is an FDM or FFF, fused diffusion modeling, or aerosol jetting, or SLA, whatever it is, we are converting into a STL file, stereolithographic file. That is very common and easy to make it. Then after that, that STL file will be transferred to the 3D printing machine. The machine will build that the component layer by layer. Then after that, we have to remove the machine from the bed, and unwanted part will be removed with the help of either by hand or by using chemical washing. And after post processing, we will be able to get our finalized product. So the making a CAD model is very much important for all the 3D printing system. We have to make a STL format. So what is STL format mean? Whatever the object you want to make it using AM, you have to convert into STL file. That STL file generally uses a triangles to describe the entire surfaces of the object to be built. Each triangle is described with the help of a 3 point and a facet normal vector indicating the outward side of the triangle. The similar way, each and every facet of the triangle is actually prepared with the help of a STL file, and that will be transferred to the printer for printing. So, so far, what we have discussed is what is 3D printing, main difference between subtractive and additive manufacturing, what are the various techniques or methods available for 3D printing. Out of that, most commonly used three 3D printing technique like SLA, FDM, SLM. We have seen it, and also we discussed about the various steps involved in 3D printing of any objects. Okay. So next we will be moving on to our research area. Um, 3D printed RF energy harvester for IoT application. We have executed a couple of projects and we made some 3D printed antennas also. So before going into the 3D printed antenna, we need to know about what is IoT and what is the need of energy harvesting application. Okay. So first, let's start discussing about what is IoT. So recent technical developments on low power devices are capable of connecting the entire world through internet, and they are forming the key elements of the Internet of Things. The Internet of Things, shortly called as IoT, is based on large number of interconnected devices, and they are capable of communicating with each other information. They can communicate with each other and also pass the information to the network also. Nowadays, the billions of devices are actually available in our day-to-day life, and they can contact with each other, and they will be providing an innovative feature solution in various area. Say for example, what is Internet of Things? Internet of Things actually defined by a different people. There is no only one common definition. The definition will be given by different people. For example, IDC will give different definition. Cisco, GSMA, McKinsey, they will have different term. But actually, the overall term is very simple. Internet of Things is nothing but a network of sensors and actuator for any specific purpose. The purpose may be of computing purpose, or the purpose may be of monitoring purpose, or the purpose may be of communication purpose, anything else. They are going to talk with each other and transfer the data into the cloud. By taking the data from the cloud, we are going to take any decision, or some other device connected in the cloud will be taking the decision. Okay. So very simply, Internet of Things is nothing but a network of physical objects and devices connected together. So why IoT is needed actually? This IoT is actually very much useful for make building and deploying application easier, faster, secure and more accessible for everyone. In our day-to-day life, actually this IoT plays a vital role. We might have heard of, for example, IoT based washing machine. There is no need of any human intervention. In foreign countries already it is available. If you go to any laundry shop, there should not be any human being or any manpower to take care of your service. The laundering machines are installed in that premises. They are fully automated and connected to the internet. As soon as you enter, there may be providing some app or something based on the interface what they are going to give you. So that app or the from the network internet platform, you can access the machine. If it is free, probably you can load the machine with your clothes, and after pouring the liquid, you can close it. The payment and everything, maybe you can pay it through your digital wallet. Once it is the amount is paid, the washing machine start working, and it shows the live update also. Maybe after you put your clothes in the washing machine, you can go and complete your shopping in the nearby mall. So whenever the washing completed, then you will be receiving a message. Then you can go on to take your clothes, take off your clothes and leave it, something like that. So these kind of the new application because of internet of things will create a lot of socio-economic development application in many area, agriculture, health sector, military, many more. And we will be in a position to efficiently utilizing the manpower, so that the power can be saved, water can be saved, the human resources can be saved, so that we can have a lot of, if we use IoT. So different type of application. The one of the application I told you, your fridge can be controlled using this IoT. For example, you can just set your fridge temperature without, by using app itself. You can control. The fitness tracker is one of the mostly widely used application. Everyone of you nowadays using a fitness band or smartwatch. How much walk, how much steps you walked per day, what is your heartbeat, blood pressure, many things can be monitored, your stress level, your everything, and it communicate to your app. Then you will be directly taking the data, so you can review that your plan and do it. So the similar way, with the help of IoT, the patient can be monitored from the remote places or stored. It can be given. So like that, unlimited application in everywhere. So one small comparison, in 2010, actually the number of IoT connection is very less. But if you look up here, it is increasing to 30.9 billion devices are roughly connected at present. So now the IoT is actually dominating the non-IoT smartphone, laptops, and computer compared to the non-IoT. In future, everything is IoT based control. We can't imagine. Main challenges of IoT technique is actually the sensor. The sensor should be very small size, and also they have to consume less power. Similarly, transceivers also it should be very small size. It is affordable for everyone to buy that, and also it should consume power consumption. So the main between receiver and it's a power autonomy. That means the power consumption should be very less. The battery is having a limited lifespan, so we have to periodically recharge the battery. So in some of the location, actually reaching the IoT sensor itself is difficult. For example, in hazardous places, suppose you are placing your IoT sensor for air quality monitoring, something, but that area is not reachable. So it will be very difficult to charge the battery. Okay. So what is the solution? So for that, actually, we are going for harvesting. So the power requirement of IoT devices, it will be varying. Say for example, if a desktop, maybe we require 100 watt, laptop means 10 watt. Suppose your IoT devices like electronic watch, it will be requiring maybe 1 microwatt, very less, varying watts. Okay. So it depends on our system. We may require a energy which varies from 10 nanowatts to 100 watt. The most of the IoT devices are going to operate at a very low power level because they are constructed using low powered electronic devices. So even though they are consuming very less power, there is a need to charge them periodically to provide uninterrupted services. So that's why the concept of energy harvesting came. So energy harvesting is nowadays very very essential to nowadays we are talking about zero consumption, zero emission, energy conversion building, and many more. Why energy harvesting? Electronic control system mainly rely on the remote sensing for its reliable and efficient operation. Lot of energies are actually wasted. Even if you consider at present, there are a lot of electromagnetic energy in and around us. There are so many cell phone signals in and around us, and also there may be a signal coming from Wi-Fi devices. There may be some signal coming from laptop, or the signal coming from satellites, or the signal coming from FM radio, AM radio, like that. There are so much signals are in and around us. Okay, so those things actually have to be effectively utilized, so we can charge the with the help of conceived from the environment. So what are the sources of energy harvesting? We can harvest the energy either from thermal energy or chemical energy, nuclear energy, solar energy, wind energy, or even piezoelectric energy. We can harvest the energy. In addition to that, we can harvest the energy. Those are conventional sources. Okay. So this RF energy also we can actually harvest from either all our digital equipment, because all our digital equipment will radiate it, or they may be operating with some RF signals, no doubt at all. So we can harvest energy from various devices with the help of different cells. That radio frequency energy we can harvest with the help of a device called antenna. All other things are transducer, you know that. Similarly, we can harvest the energy from radio signals with the help of an antenna. The power varies from very small, 0.01 to zero point 0.1 microwatt only. But there is not a single energy source satisfying all the needs of IoT devices. So always we can rely on the multiple sources. Suppose if solar power is not available, we are in a compulsion to use the thermal power, right? Suppose if the power cut in our home, obviously we need to use the battery. In that the inverter, in that inverter already energy is stored. So whenever the conventional electrical power is not available, we are going to use our UPS power. So something like that. We have to power up this IoT devices with the multiple sources in such a way that we can maintain the IoT devices always on. So radio frequency energy harvesting means we are going to harvest the energy from the ambient radio frequency sources, maybe from mobile station or Wi-Fi transmitter, or from mobile phone, laptop, TV or radio transmitters, or even signal from walkie-talkie, anything. Okay. So first we need to have an antenna. Then after that, receiving antenna, we have to use the matching circuit and rectifier circuit. Then we can power up the any of the low power electronic devices, for example temperature sensor, or we can charge our micro camera, or maybe a hearing aid, anything we can charge it. As I told you already, there are various varieties of sources. Something may be intentional, something may be unintentional or anticipated. Subtic may be unknown. Intentional means the devices what we are, those are intentional. Anticipated mean other devices they are not intentional to radiate, that may not be working. So from those three energy sources, we can harvest the energy and utilize to charge our IoT devices. Similarly, on opposite term, actually wireless power transfer. So nowadays the phones are coming with the wireless charging. So in that actually the electrical power is transferred with the help of a near field technique. So RF energy harvesting is a far field technique. The wireless power transfer is actually a near field technique. So near field energy, we are going to charge our devices. The difference between at the expense of energy and cost. So RF energy harvesting system, existing RF sources, we have a channel. From the RF energy harvester, we are going to convert the energy and we are going to power the IoT devices. But if it is a wireless power transfer system, we are going to use a dedicated RF source that will generate energy. The same setup, RF energy harvester we will be using, and that will charge the IoT device. So very simple. The difference is here we are going to use a dedicated RF sources for charging a battery of IoT devices. In the previous case, energy harvesting case, we are going to use the existing RF devices from multiple ways, multiple sources. We are going to charge the IoT devices. So this is the general architecture of IoT system. We have a multiple channels, multiple sensors. All are providing analog information. We are converting into that digital information with the help of ADC, and the microcontroller will be collecting the information. It is a very low power microcontroller. We are not going to do any programming on the IoT side. Every computation monitoring will be done at the cloud or server side only. So here that IoT module will simply collect the information and then process it, convert into a digital one, then transmit that information to the nearby cloud or nearby relay with the help of either Wi-Fi or through wire. So different method can be possible. Either it may be communicating through wires or it may be communicating without wire, depends on the application and those information stored in the cloud. So here the various, so when you look at that, the temperature sensor will require the voltage of 2 to 3.3 or the power required is 400 microwatt, but a smartwatch require 1 megawatt. Now, suppose if you are using a glucose sensor, it requires the power consumption of 3 microwatt. So something like that based on the IoT device, how much power it is required. First of all, we should have a clear idea about that. Based on that, we have to build our energy harvesting circuit. So this, I think time is running. I'll quickly finish it. So this is the block diagram of the radio frequency energy harvesting circuit. We have an RF generator that may be any source coming from the various. There will be a free path and the receiving antenna will receive it. Then impedance matching network will match the rectifier out the antenna output to the rectifier input, because to ensure the maximum power transfer from antenna to the rectifier, which will convert the AC signal into DC signal, matching should be done. So the matching is very important. We have to very carefully design the impedance matching circuit. Then thereafter we are designing the rectifier, because the voltage obtained from this ambient RF sources are very less. They are not very much high compared to that other energy sources. So we need to use the voltage doubler or voltage multiplier also to improve the signal energy. Then once the voltage is reaching the sufficient level, then we'll be using the power management unit that is responsible for charging the various IoT devices. So while considering the radio energy antenna, we have to use the and orientation. So these things we have to check. So matching network, we have to so consider about the network topology, what we are going to use, which one will be suitable for our frequency, what is the bandwidth. If bandwidth is narrow, we will not able to get a maximum efficiency. If bandwidth is very wide also, it will be difficult. it will just try to acquire energy from some noise sources also. So that has to be actually carefully chosen and based on the dielectric laws also. So these are the different type of impedance matching network: L network, T network, pi network, reversed or inverted L matching circuit, and so on. They will be useful for matching a antenna circuit with the rectifier. These are the rectifier. We can use either half wave, full wave, or bridge rectifier, but these will only rectify the signal, but not suitable for increase the magnitude. But magnitude will be very very small in the case of RF and harvesting. So we are compelled to use the voltage doubler or multiplier. Okay, so different classifications of multipliers are available, voltage doublers are available. So out of that, anyone we can choose, so that we can fabricate a radio frequency energy harvesting system which is conventionally fabricated. That is, here the antenna and the energy harvesting circuit is constructed using the simple subtractive manufacturing technique, nothing but PCB based manufacturing, printed circuit board based manufacturing. So here they will be achieving a conversion efficiency of up to 60, not more than that. That based on the load, it may be varying it. It is one of the good circuit which can work for broadband operation. Actually, here they are using two different two-stage rectifiers, so it will give somewhat reasonable amount of energy conversion from radio frequency to DC voltage required for any sensor system. This is also example of the one more batteryless temperature sensor application designed for a real-time application. The left hand side we are showing the antenna, the rectifier is at the bottom, so antenna will collect the signal, and the rectifier and matching circuit combination is at the bottom. So they will convert the RF signal into a DC signal, and that will be given as an input for the temperature sensor. So this sensor is actually tested in the real-time environment and the street, that how much energy is approximately some 1.9 volt is actually collected out of the circuit. But still, even still it is less, so we need to think about the way of improving the efficiency of the circuit or designing an antenna in a very good way. And also probably instead of one stage we can go for a multiple stage voltage doubler or to get more voltage. This is also one of the energy harvesting circuit. So it uses the antenna. So it uses two antenna. When you can see at the photograph on a third photograph on right, the behind that there is a one base station, and from the base station about 100 meters away, actually the circuit is tested in a real-time environment, and it is producing a efficiency of up to 55%. So when you look at that, all the designs so far we have seen it, the efficiency is actually very less. So our research focus should on improving the efficiency of the thing. So this is one of the meta surface based. So each and every cell here, they will be collecting, each and every cell will act as an antenna, and they will be producing a combined energy. That combined energy will be rectified and processed. So here, so that's why it gives a energy efficiency of up to 90% compared to that antenna based rectifier circuit used in the previous case. So what we are trying to propose is, we are trying to propose in this case the entirely 3D printed radio frequency energy harvesting circuit. So here we have used two different antennas using a single feed. We have used the T junction power divider that can harvest the energy from both the antennas. So the red color one is nothing but a 3D printed substrate made of PLA. When you closely look at that, you can see that the surface in both the cases, you can see that the surface is not smooth. Lot of lines are there. Okay, so that have to be avoided if you go for a SLA based printing. We have gone for the FDM based printing. Okay, so if you go for SLA, you will get a smooth surface. So the substrate is printed using 3D printing. Again, this that copper things are actually printed with the help of a aerosol spray method, not a jetting method, spray method. So there are two antennas, and they are two dual band antennas, The inner ring will resonate one frequency and the outer ring will resonate for one frequency. So it will work for dual frequencies to increase the uh, of the circuit. So here we will be using a matching circuit. This portion is a matching circuit. It is a dual band matching circuit. It will match the frequency 2.4 GHz and 5.2 GHz commonly available Wi-Fi frequency band we have chosen. We have used the same rectifier. It is a two-stage rectifier, Willard rectifier. It will use, it can the multiplier as well as the rectifier. Both the job it will be done by the same circuit. So this is the real-time measurement. Just for understanding, we kept this energy harvesting circuit nearby the mobile phone. You know that when the mobile phone is about to receive a call or while it is in active mode, there may be a possibility of more RF signal involved. So you can see that almost the harvested energy is 140 millivolt. But actually we want to use this 3D printed technique for IoT devices. As I told you already, the IoT devices are very small. For example, sensor and along with the communication equipment. So we can use this 3D printed energy harvesting circuit as a housing unit for the IoT element. So in the previous case, the antenna is printed on a plane surface. Here it is printed on a conformal surface. On the outside, the rectifier and antenna both are printed. The whole circuit is 3D printed, and we kept that IoT module inside that the energy harvesting unit. So this energy harvesting unit will act as a housing for the IoT module. So it will provide the protection against the environmental changes. At the same time, it can act as a housing or envelope for the IoT sensor. So it is producing a the very good the conversion efficiency, and it is reaching up to 90. But for 5.2 gigahertz, the conversion efficiency is less because when you look at that, the matching at the circuit is not that much perfect. So the improvement has to be done. The same way, we have designed one more energy harvesting circuit that uses actually metasurface based one that will give the more energy compared to the conventional one. So that is under process. I am not showing it. So already time is reaching up to 7:15, so probably I can give you 15 minutes for any questions so that I can clarify. So apart from that, currently we are working on this the same 3D printed fluidically reconfigurable devices. With the help of the tuning can be normally done with the help of an antenna. Sorry, with the help of a diode, whether it is an antenna or power divider resistor, whatever it is. So the switching can be done with the help of rectifier, but instead of that, we can do the same switching with the help of liquid-based devices. We can use water or we can use acetone, or even sometimes if we want to change the frequency of an antenna, we can tune the antenna with the help of a liquid metal. Actually the liquid based things are very much useful for very high power application. And also they will, in order to switch on the diode, we need extra power. In addition to that, we have to draw the number of connection line in the circuit, so they will create some electromagnetic interferences. So those kind of problems can be eliminated if we go for a liquid tuning. So the work is currently under progress. Apart from that, we have made the recently the 3D printed horn antenna and 3D printed lens antenna also. Since the work is classified, I am just not putting it here. We have some limited facilities, but having collaboration with that other universities, actually we are trying to print even metal based RF component also. For example, like waveguides and other things. Those works also in progress. So with this, I can conclude. So if you have any doubt, maybe I will try to clarify best, because basically I am not a mechanical person. So related to that internal parts, I'm not much aware of that, but we know how to for our requirement. So if any questions, probably you can post, or you can reach me in my mail ID also.
Thank you, sir. Participants, if you have any queries, you can unmute yourselves and ask.
Hello, sir.
Yes, ma'am.
Sir, which type of antenna is commonly used in the case of RF energy harvesting?
So, pardon, ma'am. I'm not hearing
Which
you.
type of antenna is commonly used or used in the case of RFEH?
No, actually, there is no. Uh, it should be a particular antenna. It depends on the application. Only thing is the antenna which you are going to use it for RF energy harvesting application. It must have a very good high conversion efficiency. That is very important. And
Okay, sir.
another thing is you have to harvest the energy from various angles because we don't
Okay.
know, because though all the RF energies are uncertain, they may come
Oh,
from 360-degree direction. So if
okay,
you
sir.
go for a circularly polarized antenna, you can increase the efficiency.
Okay,
Okay.
sir. Okay, sir. Thank you,
So
sir.
according to your application, actually you have to choose it. So your
Okay.
RF energy harvesting antenna should
Mm,
should or must have a very high conversion efficiency. If it
okay.
is not possible, you have to look for other techniques to increase the frequency by using meta surfaces or FSS, that kind of thing.
Okay, sir. Thank you, sir.
Thank you. Just a minute. Another 10 minutes. I'll come. Wait.
Any other queries, participants? So, how to choose that effective materials for those meta surfaces and also?
Ma'am, again, it is depends on the frequency only. Meta
Okay.
surfaces mainly it is based on the structure orientation. Okay.
Okay. Sir.
So
Okay.
compared to material, you have to focus on the structure. Normally, you have to choose the material which are having very less lossy. That is
Okay.
very important. But suppose if you want to create a meta material, meta surfaces using 3D printing technique, obviously PLA and ABS, those are having very much lossy only. So that should be a compromise.
Okay, sir. Okay. Okay, sir. Thank you, sir. So, any other queries? So, okay, sir. So, thank you, sir, for accepting our invitation and sharing your valuable knowledge in additive manufacturing. And your expertise help us to understand the applications and various techniques in additive manufacturing and also about energy harvesting circuits. Actually, the session is very useful for the researchers to explore the research opportunities and also for academicians to share the knowledge they have gained with the student community. So, thank you, sir.
So
Thank you.
thank you, ma'am. So thank you, participants. So if you have any doubt, you drop me an mail. And also, I thank that references and the diagrams I took it from the Google. So I'm just giving thanks for that unknown as a part of this lecture. Thank you.
So,
Thank you, Dr. Karthikeyan. This is Dr. Durga Devi. Thank you
Yeah, good evening.
thanks for accepting our invitation, sir. Thank you.
Yeah, thank you, ma'am. Thank you, ma'am. Just I'm leaving.
so participants, kindly switch on your video for taking a photo.
Ma'am, I leave, right?
It's for 1 minute, 1 second. You just switch on your video. We'll take a snapshot of it. Sir. Then you can leave, sir. So
சார் ஒன்றும் இல்லை சார்
participants,
மீட்டிங்கில் இருந்தேன் நான் வரேன் இப்போ. இல்லை சார் நான் இப்போ
participants.
நீங்கள் ரெடி பண்ணி வைங்க. இதோ வந்துடுறேன் நான். இல்லை சீக்கிரம் வந்துடுறேன்.
So kindly switch on your video, please. So okay, sir. Thank you, sir.
Okay, ma'am. Thank you, ma'am.
Thank,
Thank you.
thank you, sir. So we'll start the next session by 7:30. You take some 10 minutes break and kindly join on time. Thank you all.
Good evening to all. Topic of this session is smart sensor and embedded system for real-time monitoring. Now I call upon Ms. Sheba ma'am, Assistant Professor, ECE Department, for giving brief introduction about speaker Dr. S. Madhava Pandian sir. Sheba ma'am.
Ma'am, is it audible? Ma'am?
Yes,
Yeah,
ma'am.
ma'am.
Yes, ma'am. It's audible.
Okay,
Ah.
ma'am. Okay, thank you, ma'am. Good evening, everyone. Dr. S. Madhava Pandian is a seasoned professional in the field of embedded systems, currently serving as director at Tara Systems and Solutions, Bangalore. With over 15 years of combined experience in industry and academia, he has made significant contributions in the domains of embedded system design, skill development, and curriculum innovation. He holds a PhD in embedded systems from Anna University, Chennai, a master's degree in embedded system technology from Raja College of Engineering and Technology, and a bachelor's degree in electronics and communication engineering from Coimbatore Institute of Engineering and Technology. Prior to his current role, he served as a design lead at TESOL Chennai for over 6 years, from 2018 to 2024, where he led multiple initiatives in learning design, instructional strategies, and skill enhancement for engineering professionals. Earlier, he spent over 8 years at Akshaya College of Engineering and Technology, serving as assistant professor and head of the department, actively involved in curriculum development, academic administration, and student placement coordination. Dr. Madhav Pandian's core expertise lies in embedded system design, skill and curriculum development, instructional and learning design, pedagogical innovation in technical education. His academic and industrial journey reflects a strong communication to bridging the gap between theoretical knowledge and practical implementation. His leadership continues to inspire innovation in the embedded systems domain. Welcome, sir.
Sir?
Oh, thank you, ma'am. Thank you for introducing me. Uh, so it's a pleasure to share my experience to all the faculty members from various colleges. And I'd like to thank the New Prince Bhavani College for inviting me in the session. So I guess it's almost late. We have planned for 7:30. We have on the skip faculty. I hope I can start my session. So I'll just share my screen. I hope my screen is visible to everyone.
Yes, sir,
Visible,
it's
sir.
Yes.
visible.
Thank you. Thank you. So, thank you for introducing me, ma'am. Excellent. Thank you. So, today my session plan is regarding sensors and how embedded systems are used for real-time monitoring part. So it's a quite a larger area. So it almost covers all the topics which were already done and also what the topics which are going to be there in the future coming sessions also. So I might have overlapping of other sessions also in the part. Just an introduction about Taurus. So we have been associated with New Prince Bhavani for quite a long time, and it also previously my TESOL. I was working in TESOL, and we had a very good relationship in academic council, and also we had some skill development programs there. So Taurus, we focus on three major areas mainly. One is regarding bridging the gap by skill developing to colleges, and next we have a division called as step to startup, sorry, step to hire, contract to hire, sorry. So wherein we have employees with vast experience, so we give them to clients and for project development. And third, we also do the skill development for people of experience also. So these are things we focus at TARS. And about the session, so I will focus on smart sensors and how the sensors are selected based on the requirement and how it is to be changed in the forthcoming years in other domains like Industry 4.0 and the Edge AI, how it is going to be there is my focus today. And I will also like to show some stimulation kind of thing so that you can have a hands-on experience on how this is going to be. That's what is my plan for today's session. So first of all, let me just give a broad area. What we are going to focus is about sensors. Right? So might be a repetition of the same content. These are going to give us some data based on the physical environment in form of voltage or current or some data. So generally what we use in sensors is we get the electrical signals by processing it, we get some data. So there are different kinds of sensors as you can see there. We have longitude, altitude, voltage, motion, temperature. Like this, there are different areas. So this is the base, what is our interest of today's session. So first, let me give a classification on how sensors are going to be generally made. So sensors are generally classified into four categories. First is regarding the output signal, and next is regarding the measurable quantities based on power requirement and contact type. So these are the broad classifications of sensors. First, let me discuss about the output signal type. So generally, based on output signal, it is classified into analog and digital. So when I consider about analog, that is the most used lower cost sensor. And most of the cases, we would prefer analog sensors because that availability of that is already there in a lot of places, and most of the industry or earlier industries which were using had analog sensors. And there are some factors where we don't have a digital sensors also. Like at a very high temperature range, we don't have a digital sensors available. So that is the case. So about this analog, we'll be getting a continuous voltage or current signal. Whereas if you take about digital, we'll be getting a discrete value or a packet of data. Now, whenever you use a analog sensor, what we require directly is we are going to measure a output magnitude, which is going to be equivalent to the physical quantity which is measured. Whereas here we would be having an onboard microcontroller with an ADC. So the data are going to be processed, and finally we'll be getting a digital data there. So when we have a analog sensor, there is a requirement of ADC in the pin. So when we have an ATC, there is one more factor of resolution. So generally, what the basic level resolution which we get in the market will be in the range of 10 bits. So then comes 12 bits. This is what we generally get in the market at lower cost. But there are situations where we require a resolution up to 24 for getting a better value at the output. Next, when we have digital sensors, so we would directly get the data. We can directly interface using some communication protocols like SPI or I2C or UART, or even certain things are available in Ethernet or module also. Or in some cases, we can directly have a GPIO for binary signals. When we talk about noise immunity, analog signals are more prone to errors, and possibility of rectifying the errors is very difficult, or identification of errors is going to be very difficult in case of your analog sensors. Whereas comparatively in digital sensors is going to have a higher noise immunity. We could identify the errors, and we can also reduce the noise part, and we can also get the accuracy comparatively more depending on certain factors like comparison. We could get a better result in digital sensor. Uh, in case of analog sensors, there is a particular value range which is available, where we would have to do some processing and we would be getting the data. Here in digital sensors, we'll be getting the output pre-processed, and so that we can directly have the data and process it. Considering the college level projects, I've just taken these sensors, though we are mostly avoiding these sensors because of two main reasons. One, it will not be as required output because the error percentage is quite higher in these sensors. So generally, we don't use it for industry applications. Just for consideration, I've taken these sensors. So in case of analog sensors, we give it generally which is preferred, or what is done in college syllabus. Generally, we have this LM35 sensor that will be giving the temperature and LDR for right, and MQ2 gas sensor, and a pot or potential meter. So digital sensors, mostly it is there on DHT22 or DHT11. That will directly give us the temperature and humidity. And similarly, we have MPU sensor for motion and IR sensor for obstacle detection. So these are the basic things classified on the output signal. Moving further, so this is the case where we choose what. So, for example, we choose analog sensors when the application is simple, and certain case it is a critical application. We generally prefer analog. So when we want the longer distance runs, for example, in an electrically noisy environment, we have this 4 to 20 milliamps is generally used. And one more reason we prefer this uh, analog sensors is the previous existing infrastructure will be there on analog input output cards. And the cost of primary drivers for smaller points will be present personally used there. And most of the cases, persons are only trained for using the analog systems in most of the industries when we are planning to automate. Next comes the digital sensors. So with the output of IO link or field bus. So here we would be getting a rich data beyond a certain value. So that would be used for diagnosis, parameterization, and even tracking. So then comes the installation of sensors. So the wiring cost are going to be involved in that also. So in that case, we'll be preferring a digital sensor. We could even have a multiple sensor modules also. Next, we have a flexibility and remote management. So wherein the data are transferred directly. So we would we don't have to plan on the other factors. And we would be getting a higher precision resolution. And whenever we prefer to use Industry 4.0 or IIoT facility, so wherein it is integrated to a data facility or some service, we would be preferring digital sensors. So that's the thing where we would select the sensors based on the requirement. Next classification, which I would like to have, is on measurable quantity like temperature, where it would be measuring here, whether it's hot or cold, like we would be using LM35 or DHT11. Pressure, generally ABMP 108. and proximity like IR sensor and ultrasonic, light density like LDR and TSL, motion sensors or motion like PAR and accelerometers, gas concentration we use MQ2 and MQ135, and humidity in air we would be using DHT11 or 22. So these are the classification based on the measurable quantity. Next is based on power requirement. So, for example, we would be requiring an external power to operate in ultrasonic or IR sensors. And certain sensors, they would be self-powered like thermocouple or LDR. These would be self-powered where we don't require an external power to work with. The last classification is based on the contact type. So generally, the contact types where we need to have a physical contact like thermistor and tactile sensors, and non-contacts are generally preferred because we don't have to give it on or put it on a particular subject. So wherein we have IR, ultrasonic, and radar. So these are the things based on the contact. So these are the basic classifications which are there on sensors. Moving further, now why we will require to go more to your smart sensors or the sensors with direct data correctly is because we'll be getting the process data and we don't have to concentrate on processing the data, wherein we directly get the data using the communication protocols like I2C, SPI, UART, CAN, etc. And about intelligence, there's no intelligence, or we need to add intelligence to that device by processing the data. Whereas the smart sensors will have built-in microcontrollers or DSP process to process the data. So that's an example of traditional and smart sensors. So BME 208 will be giving temperature, humidity, and pressure directly, which would be used for applications. And next part, we should also concentrate on the actuators, not just sensors. The next part is also important is actuators. So wherein we convert the electrical to physical actions by controlling motions, pressure, temperature, or mechanical systems. So these are generally paired with microcontrollers for automation and controlling some systems. So again, the process of selection is based on the following factors: the control signal type. Mostly when we have actuators, we would be using PWM or the analog output which is required or on-off type, and whether we require torque or force, whether we require some feedbacks, wherein we would go for a servo or a normal motor, power source, whether we want internal or external, and safety factor is another important role in case of automation, is whether we have limit switch or overload selection so that we don't damage the actual machinery or other things. So these are the classification of actuators. One is source of energy, motion type, control signal type, and application domain. About the energy source, so we would generally use electrical when we want some motions done in electrical way, like DC motors and round coils for automation and also controlling something. We use this. And next is hydraulic based, wherein we use compressed or pressurized fluid to move object here. And next comes pneumatic, where we use compressed air, like air cylinders or valve control. Most of the embedded, we generally use the first one, electrical based, like DC motors or solenoid valves. That is generally preferred. When you want to have a larger thing like you want to be moving it, we would prefer the hydraulic or compressed air or pneumatic. Next is motion type. We classify based on linear and rotatory. So this is going to work in a straight line of motion, like solenoids and piston actuators. And next is some rotatory, where it is going to produce a rotatory motion like servo and DC motors. And about the control signals, first is analog control, where we'll be controlling using voltage or current, so like dimming control motors, and digitally controlled by using on-off or PWM signals like servo motors or relays. Next is about smart actuators, where it will be having a built-in processor unit where we can use for smart servo or stepper drivers. We can use that and control the devices. And next, the common electrical actuators, which are generally used are these, like DC motors, where we want electrical to rotational motions for fans, wheels. Servo motor, which are again controlled rotation with the feedback part. So we'll be using at robotics, RC vehicles, and stepper when you want a precise step-based rotation, which are 3D printers and CNC machines. And solenoids, when we want electromagnetic linear movement like locks, valves. And next comes relays, where these are electrically operated switch. When you want to use or control a high voltage circuit, we'll be preferring the relays. Before moving on to the embedded, we need to know the basic thing is the end devices. So this is one of the important parts because these end devices are connected to the sensors actually too. We water part, these are the things which are there at the physical world, which are directly there. So the work of this would be on input side and output side. So input side, these are used to gather the data, might be from multiple sources or multiple data are gathered like temperature, light, pressure. And there are output devices like actuators, which perform some actions like some motors, LEDs, displays will be using it. Next, these are the simplest end devices which are used for a very small level controlling. Some of them is given, mostly we'll prefer an 8-bit processor at this level, which are connected to a sensor level or smaller level controls. So these are generally used in switches and basic sensors and small actuators. These are used. So in that case, we have a 80 tiny 85, which is a very small. There are around 8 pins in that. So it's a 8-bit processor, which is a smaller size, and there's going to be very few GPIOs there. So these are generally used for LED controls, temperature loggers. Next is PIC from Atmel or Microchip. So these are 8-bit, again, very low cost. These are used for simple logic controls. Next is a STM's 8-bit part. So these are generally used in IR remotes and basic appliances. And next end devices, which is there is a wireless end devices, which are generally used for IoT applications. So these are actually going to communicate wirelessly to the next devices or multiple devices will be communicated. So generally in the market, we'll be having, or some of you might have even used the Node MCU or ESP8266. So these would have a Wi-Fi with 32-bit and lower cost. So this is used for smart plugs and Wi-Fi sensor interfacing. Similarly, there's ESP32, which has a dual core, and also it has onboard Wi-Fi and Bluetooth. So these are generally preferred for smart home and wearable devices. Next is NRF microcontroller. So these are having a Bluetooth, and these are based on ARM Cortex M4. So these are generally used for fitness trackers or BLE or Bluetooth platforms. We'll be using these things. And next is CC3200. These are again ARM Cortex M4 based uh, controllers. So where it is going to have a onboard Wi-Fi. So these are generally used for IoT nodes or home automation. And next end devices are battery powered. So which would be generally of a lower per consumption part. So these are generally used for wireless sensor networks or remote sensors or wearable devices. So some of the examples are given here from TI, it's MSP 430. So that is ultra low power, 16 bits. So these are generally preferred for environmental sensors. Next is Atmega, which is what is there in Arduino microcontroller or Arduino Uno. So it's the 8-bit ADC, UART, SPI, I2C is there. So Arduino based generally these are used. Next is STM32 L2, L0 series or L4 series. These are very ultra low power microcontroller based on ARM Cortex M0 or M4 based. So these are generally used for medical and industrial sensor part. So this is a thing which are used in the sensor area of microcontrollers. And next comes the actuator control devices. So these are end devices which are used to control some motors, servos, or relays. So some of the microcontrollers are shown here. So whereas Arduino Uno, which is again based on Atmega 328P sensor. So it's a simple PWM and GPIO is will be there. So these are generally used for servo or relay controls. Next is STM32's third-party version of Bluebell. So this has comparatively a faster PWM and a DMA based motor control. And finally, the big 16 series, so which has a onboard CCP module and it's going to be 8-bit. So these are generally used for industrial automations. And next are those in the category of advanced end devices, where we would be using them for AI, audio, and video processing. It is also being used in camera modules, smart speakers, and advanced sensors. One of them is ESP32S3 version, so which has an onboard AA access, USB, Bluetooth, and Wi-Fi. These are generally used in voice recognitions. Next is Raspberry Pi Pico or RP2040. So this is a dual core flexible input output. These are generally used for sensors and robotic applications. Next is NXP's IMX-RT. So this is a crossover microcontroller with a higher performance. These are used for audio DSPs, camera-based systems. We'll be using these microcontrollers. Next important part in case of the embedded system is the communication modules. So these embedded systems are required to communicate for device-to-device, data logging, and remote control and configuration. So communication module need to handle data transmission within and also in some cases outside the system for data transfer and also controlling applications also. So these are some of the communication modules based on the wired and wireless part. So some of the communication modules which are generally used are UART or universal asynchronous receiver transmit. And in some cases, they'll be also using USART or we should be having the synchronous part also. Next is SPI, I2C, USB, and CAN. So these are the basic things which are used in wired part. And first three are mostly available in all the microcontrollers which are there in the market. UART, SPI, and I2C. USB and CAN are restricted and we would require to ask from the manufacturer to use it or implement. Wireless, there's very few microcontrollers which have onboard Wi-Fi or Bluetooth. And there are also some microcontrollers which has LoRa module or LoRa facilities and GSM modules on board also. Similarly, we use Zigbee to communicate or create a mesh. Mostly in the wireless part, we'll be having separate modules to be used. So these are the communication modules. So as said earlier, so you want as a synchronous module. Generally, these are used for point-to-point GPS, Bluetooth serial data. We'll be using it. I2C is generally used when you want to have multiple masters and multiple slaves. Mostly these are used for sensor interfacing and memory interfacing, and in some cases adding or connecting some other microcontrollers also. So theoretically, we can connect up to 127 devices or connect 127 devices at I2C. But there are around 120 which we can connect as per the limit which is available. Similarly, SPIs or serial peripheral interface. So these are going to be comparatively higher speed than UART and I2C, since it's a full duplex communication. These are generally used for SD cards and displays. But mostly we have stopped using SPI in a lot of applications because of its complexity and it could only support very few slaves. So that's the reason generally in applications we would restrict the usage of SPI or SPI. And next most used part is USB, wherein when we want a high-speed data interface like USB CDC and USB HIDs, we'll be preferring this USBs. And similarly, whenever you prefer to use an application in automotive, we'll be using this CAN protocol. And in some cases, we have also started using in industrial applications also. So these are reliable multi-node based communication. Other than this, recently there's a research going on, or still we have not fully, or the microcontrollers don't have that. So research is going on, or it might be in a couple of years, we might be getting I3S things. That's also a communication module, which are yet to come to the market or coming in the other microcontrollers. So these are the communication modules which are used in the wired part. And wireless part, so we'll be having this Wi-Fi. So wherein we'll be using in node MCUs and ESPs for high speed or longer range. Mostly these are used in IoT application or smart applications. And next comes Bluetooth part. So these are generally used for a shorter range and lower power in wearables and phones. Next is Zigbee. So whenever you want to have a lower power mesh networking, we prefer the Zigbee, and these are used for automation and sensor networks. Next is LoRa. So it's actually wireless or RF based communication. It's going to work at a longer range in the lower power. Mostly, there are a lot of applications created in agriculture and rural IoTs where the network availability is very less in that area. And the last is GSM or GPRS. So these are generally cellular based, which are used at remote data communications. But what happens here is the reliability of these devices or GPRS or GSMs are very less. So generally these are avoided at the places where the network availability is very less. So these are the things which are available at wireless communication models. And next comes the gateway model. So these are the nodes that's going to connect the embedded system and all sensor networks to external networks. So it's going to translate or it's going to act as a translator between different communication protocols. So these are generally used in IoT, industrial automation, and remote monitoring systems. So these are the roles. So it's going to be an aggregator of data from end devices. It's going to perform pre-process or filter things. These are going to be connected to cloud platforms or servers. So there it also might act as a bridge protocol between UART, Wi-Fi, Zigbee, Ethernet. So these are the roles of a gateway module. So these are some of the gateway devices which are used in embedded. One is Raspberry Pi, so wherein we can use Wi-Fi, Ethernet, GPIO, and Linux part. So these are used when we want edge processing or protocol bridging. Next is ESP32, where we could be using Wi-Fi, Bluetooth, and low-cost applications. We could use for local sensor network gateway, BeagleBone, that is used as industrial data aggregator. Arduino plus GSM could be used for remote area data logging. And industry gateways like Advantech and Monex are used for rugged and protocol-rich application where we can use it for IoT or SCADA integration. We can use this gateway devices. So this is a broad overview on what are the IDEs which are available depending on the microcontroller and what we could use. So Arduino IDE, it's quite famous because they have a lot of examples given and they have a lot of created backend applications for that. So which would support Arduino's versions like Atmega, SMDA, ESPs, and it also supports some of the STM modules and some modules from TA also. Arduino IDEs have been modified. So these are used for simple beginners and larger communicating. Then, in case you want to have an advanced version of that, you could use a platform IO, which could be used in your VS Code integrated there. So can support almost all the microcontrollers, whichever is there in the market. So which are advanced and is VS Code based. It's going to support multiple boards. Next is STM. So these are generally preferred for STM microcontrollers only. So there are two options to program here. One is gate level or register level, and also code generation is done in that. Next, we have MP Lab, which are generally supported for microchip. Similarly, we have Atmel Studio that is generally used for your AVR or Microchip also is supported here. Next is Keel. Keel are generally supported for all the ARM process like NXT, ST, TI. All the things are supported here. So we should support RTOS, EMSSI support, and register view. All these are possible. Next is IR embedded bench. So this again would be supported, or this is third party software. It almost supports all the microcontrollers. It's generally used for industry grade tools, and it's going to have a higher optimization there. Next is Code Compose Studio. These are generally for TI microcontrollers. Next is Sega, that is generally used for display processors and ARM products, which are lightweight and is going to be free for commercial, non-commercial use. And finally, in case we work with FPGAs, we might be using Xilinx or Vivado for Xilinx, Zinc, and FPGA boards, wherein we could use it for embedded plus FPGA integration. In case we use Intel boards, we could be using a software called as Quadras. So these are the things which are available for programming those microcontrollers. So ID selection based on our requirement, we could, if you are beginner, we could be using Arduino or Platform IO. If you are going to use STM board, we would be preferring CubeID or Keel. In case we work with PIC or AVR, we need to use MPLab or Atmel. And if we want to do a professional ARM development, we would be using IAR, Keel, and Sega. IAR is used in a lot of industry, or we are already used, or we use that for our application development also. There is also a cloud development option also in Arduino. And similarly, Kale have or ARM have their own compiler online, is embedded compiler. So these are the IDs which we can select it for create an application in embedded system. Now comes the key criteria which we require to select a microcontroller, a sensor, and also use it for real applications are these. So first is electrical compatibility. What is the voltage and current rating? Whether that could be used for our application. The GPIO pin requirement. How many GPIO pins are required for applications? Interface protocols. Whether you want digital like GPIO, UART, I2C, and SPI. Whether you want to have ADCs. How many ADCs we require there? Power consumption is a major area which we need to concentrate on embedded system because most of the embedded system application happens using a battery operating system. So we have to essentially consider a microcontroller which is going to consume lesser power and also has a low power load. And next comes the response time. So these are very critical for real-time applications. So wherein we would require the response time to be at a much faster time. And also the environmental constraints. So we need to consider that for temperature, humidity, vibration tolerance. So most of the mechanical movement parts, we need to have that vibration tolerance. Because if we don't have it, we might not get the required output at that time. So next thing which we need to know is using or moving on to the next level, pushing the data to the cloud. So mostly whatever we generally using till now is based on cloud computing. When we use cloud computing, we have some drawbacks in that. The first and most important drawback is the latency part. So we have a larger latency depends on our network connectivity and connectivity to the server or the cloud. That's a major challenge there. Next is bandwidth. The amount of data is consumed is going to be very large. Next comes the security and privacy concerns. That's also a major challenge which is there. And mostly these are not ideal for real-time applications where we require a faster response time. Since we need to concentrate on that, we generally avoid this in your cloud applications. Right. So wherein might be this topic might have been taken yesterday, where we have to prefer for edge computing. So what is going to happen? These are data is going to be processed near the source or the IoT devices. So what would be the advantage? We don't have to send everything to the cloud. For example, the smart cameras, autonomous vehicles, and factory sensors. So this is a cloud architecture. So you could see this. The edge layer is generally going to be processed at the IoT device or end device itself. So the real-time data processing is going to be happening, and also data filtering is going to be there. And in case we could also move to that to fog, wherein data analytics or data reducing would happen at that area also. And finally, it's your cloud area. So wherein we would send the data to cloud, where we'll be using for storing the data or business logic or big data analytics, we could be using that. So this is how the data thing is there. So these are the advantage of edge computing. So we'll be having a faster response time for real-time applications. We would only send the essential data to the cloud, and we have an enhanced data security, which means we are going to keep the sensitive data locally and we'll only send what is required. So it's going to improve the reliability by working even now when the network failure is going to be there. And it can also have a increase in the scalability. So depending on the demand, we could add some resources in that. And the next important part in recent times is risk computing. So it is much lesser than the fog or edge. So here the data processing is going to happen almost at the sensor end itself. So this is going to be a lightweight computing. Is going to happen or in the end nodes itself or within the sensors or router itself. So this is going to act as a bridge between the end devices and cloud. So wherein we don't have to depend on a particular microcontroller could not or cannot be loaded so much because we have a restriction of the memory also in that. So we have an advantage of enhanced real-time responsiveness. And these are all often integrated with fog or edge layers. Now, this is a comparison between these three. So mist are generally located at end devices, whereas edge are generally located at the gateways, whereas fog is located at the LAN or router area. So here the processing is going to be minimal, edge is moderate, and in fog it is intermediate. The latency here is lowest at mist, low and medium in case of fog. So use cases whenever you want sensors or actuators, we could use that mist computing. Gateways will be or edge will be using smart cameras, and whenever there's a data aggregators required, we use it the fog. Now, the benefits of edge and mist are, as discussed earlier, it's going to reduce the latency, enhance privacy, since the data are only available at the almost end devices or end nodes, it's going to increase the BAT, and it's also going to reduce the cloud load, load bandwidth, and it's also going to be energy efficient. So some of the use cases where we use this mist are smart cities for traffic monitoring, industrial IoT for predictive maintenance, healthcare for real-time pricing monitoring, autonomous vehicles, and smart homes. Right? So this is the basic architecture where we'll be using this for our application creation. So as you can see, the mesh devices are going to push the data to edge, edge to fog, and from fog to cloud. So this is the basic architecture of implementation of embedded system and expanded to your IoT. Now, I would like to have a small introduction on this mist processing. So, where I would like to uh, see how the data are going to be, or how would we can use that data processing at the devices. So, that is what I'm just going to show you. I will also share the links of that so that you can also even use that and create. So let me share, stop scanning, and I'll just share the simulator tool. So I'll be using a tool called as WOPI. So wherein I would just show how a normal processing is going to happen and how that could be expanded to the lower level. Right. Fine. So I've used a online simulator, which is free of cost. We can use the basic level part. So I've used a ESP module with S3 version. So which has the possibility of even processing the basic level uh, predictive algorithms implemented. So this is a very basic thing which is generally used, uh, wherein I would be getting a data from DSP22 sensor, which is connected to a ASP module, and I will be displaying that in a microcontroller. As of now, I'm not processing the data to a cloud, or I'm not pushing the data to cloud. So what is done here? I'm is getting the data of temperature, humidity, and I'm going to tell when the temperature is greater than 10, I'm going to say it is a normal condition, and else if it is less than 10, I'm going to call it as an extreme condition. So this is how a normal embedded program is done in Arduino programming part. So let me stimulate this. So you can see whenever the temperature is there less than or greater than 10, I would call it as a normal condition. And whenever the temperature reduces to less than 10, I would call it as an extreme condition. So this is how a normal data processing is done. So in case required, we would push the data to a cloud. So which means I will always be transmitting the data. And this extreme conditions are even calculated at the cloud also. This is how we predict something. So this is how the normal microcontroller works. So we push the data to a part. Now I would like to implement the same thing in a mist computing, or I would do a normal machine learning, or I would call as edge AI. It gives different names for it. So what I'm going to do, I'm going to do the same thing using a prediction part. So I will be predicting a condition whenever the temperature is less than 10 degrees Celsius. What I'm going to do, I'm going to predict it as a extreme condition. So for this, I would be using a Python code. So wherein I will be training a model. So I've trained that using two ways. One using a normal data part, and one by giving a data in an Excel. First, let me give a normal code wherein I would be predicting whenever the temperature is greater than 10. So I'm going to predict it. So this is the normal prediction which I've used TensorFlow Lite version, right? So I'm using it using chaos. I'm predicting it. So I'm not going to say more on that because it's out of our scope to do it in just this couple of hours. So here what I've done, I'm going to predict. So whenever the temperature is greater than 10, I'm going to predict it as an extreme condition. And based on that, I'm going to create the model prediction. So I've used the TensorFlow here. So let me run this. So I've already run the whole two things. We'll let us run again. So what is the prediction is going to happen based on that is what I'm going to show you now. What is the time taken for prediction and what is the percentage of prediction is what is to be shown. I'm just running the code here. And finally, I'll be generating a model data.h file, which will be used by us for creating the code. Right. So let it run so that we can get the required prediction and what is the percentage of time which is taken for that particular prediction. Right. So in the meanwhile, let it predict. I'll show the code here. So what is done here? I've used a library file for the prediction using TinyML, which is going to take a much lesser uh, memory space to do the computing. And these are the micros which are required for that. So based on this, I'm going to use a single data. I'm going to use a single data, single output with a memory size of almost 2048 memory size is what is going to be allocated for this TinyML. So based on that, I'll start predicting. If I'm not going to get the prediction error, I'll be creating a part. So whenever the prediction is lesser than zero point 0.5 or 50%, I would call it as normal condition. Else, I'm going to call it as an extreme condition. Right. So this is based on a prediction which I made using the model.h file, which is being created. So this is the model.h file. And this is a model.h file which is created after the prediction, which I have taken from this part. So this I have done the creation. So please understand this has to be generated in a lower version of Python, which is 3.9.13. So that's the version which we need to use, or the lower version, which should be less than 3.1.0. Only that those are supporting the required part if we want to generate. So what is done here? I have predicted. I have got a, prediction of zero point 0.6. This is 0.75. This is 0.78 and 0.8. So this data has to be predicted, and I've generated this model data.h, which is available at the location as shown here, right? As shown this. So I'm going to go to the location, right? So I'm going to go to the location here. So here it is generated this file of model data. So either I could use a notepad or I could use any other ID. So this is the model data which is created for the prediction. So this is the basic data. So please understand, I've given a very small data because it will not be sufficient for the device to store all the data. So I've given a lesser prediction. So after that, let me stimulate this. So here you can see I have not done any temperature value given. So the prediction is going to happen directly based on the part. So whenever the temperature is greater than 10 degrees Celsius, you can see the prediction is going to go less than zero point 0.5. So it's going to call it as a normal condition. Whenever the temperature is going to come less than 10, right, less than 10, is going to give a extreme condition. So you can see this is not predicted properly for 9.6 because the prediction is almost 5 years. So we need to increase the data so get a better prediction. Now I've given for 8 almost. So for 8, I'm getting a prediction of extreme condition given. So this is how we could use the same thing by increasing the value. So we can also use a Excel file to be uploaded, right? To be uploaded to the device so that we could increase the prediction part also. So I just again have a small data given here. So this is the data which is given here. So you can see I've also given only 4 data. We could increase the data. So when we increase the data, what would happen? We would increase the memory size. So you can see here, whenever the temperature is almost greater than 10, I have predicted or labeled as 1. So this is how I have labeled it. So whenever the temperature is greater than 10, I would be predicting it as 1. So that the prediction is going to be there. Similarly, I could also do the prediction based on that also. So let me open that prediction part for doing it. So I'm going to create Excel data that's going to be uploaded. So based on which we are going to predict the data, and we are going to predict it whenever the calculation is on a particular range. I'm going to call it as a extreme condition or the condition which we want. Similarly, let me run the code. So you can see the prediction has happened here already, right? So whenever the case is above 10, you can find it to be normal. We have to increase the data, only then we'll get the maximum possibility here, right? So you can see the prediction is done here for the different conditions. And the prediction is not proper because we are given a lesser data. Once it is done, we have created that model.data file.h, which is again created at that particular page. And we could copy the data there and replace it. So again, we could get a prediction based on that. So we need to increase the data to do that. So this is how we could use a Python and we could start predicting it using that. There are some other tools like Edge Impulse, which is again industry level uh, platform for prediction or AI to be implemented. So there's a Edge Impulse, which is there. So we could do the processing or prediction in this tool, and we could generate data model file, which should be there, right? Which should be there, and we could use it for prediction. So there's an industry level part. So this is going to support a lot of devices like STM. We can even do it for Arduino boards also. So instead of using the prediction from Python, we could use it directly from here. And we can also predict for other higher level things like image processing, all these things, or image classification we could use. Right? So this is one tool which we can use it for a lower level. And after that, we could use this code or library file or .h file from this and start using in the file which we can use it for application. So this is how we can use that for application. So I would like to share this link. So you can just copy and paste the link at your URL, and you'll be able to see the same code running at your part. So that's a normal prediction part. And I will also like to upload a file from Python code which I have created. So this is a Python file. I share that in the chat box. This is used for the prediction. So in case if you add some more data, so you can replace it by a model.h file, and you could increase the prediction or do it. So this just for a temperature or only one value which I kept. Similarly, you could increase the number of values by increasing the data inputs and outputs here, and do it for even humidity and temperature. There's a lot of other data, and you could also use it for other devices. I have just selected this ESP32 with S3 version because it's supporting these things. And please understand, the free version will not be able to add all the library files which are there. So please, you can check the library files which are supported, or you could buy a club membership in this and use it. Or we could also use that in normal IDs like Arduino IDs. We can use that. And we could also use that in Arduino IDs, and we can write the same code in that also. And we could also use it for even Arduino, the same thing. Why I've used ESP here? Because in case in the future we could also push that data to cloud by integrating it to using Wi-Fi and some cloud platforms. Right. So this is how we use it. And similarly, all the industry level microcontrollers like STM and TI, all they have their own model zoo, which we call, right? Model zoo, which we call, for example, STM32 AI. I'm just going to search. So this is for STM32. So how Edge AI could be used for them devices. You have some materials there, and even some MOOC courses are available and how to use that microcontrollers. What are the microcontrollers which are supported, right? There will be even some sample programs also there. So this is about your STM. Similarly, TI Edge AI is also available. So they have their own Edge AI tools, right, for compiling, integrating, and you can see this. There are some Edge AI predictions, right? So these are the things which you can use it, or these are the things which are generally used for industry level applications. So you can see what are the devices which are supported, right? So how it is going to be done, what is prediction, all these things, monitoring all these functions you could just explore at this particular area, right? So there are the device which could support these, what are the devices which could be used, what is the other thing which we can use for applications, how to use it. Similarly, these have they have their own they call it as model zoo, right? They call it as model zoo, wherein they would be uh, giving a lot of pre-trained models, machine learning models, so that you can be integrating directly, like face detections, all these things, which would be having a better reliability than the normal Arduino level. applications. So you can see what different things like speech recognition, hand posture, part, all these are given here. So they have their own models. So you can find that in GitHub, right? So you can see hand postures, object detections, and even motor level predictions are there, done there. So these are device image classification, object classifications, pose estimations. So these are the things which we could use for our application. So you can see even speech recognitions, human activity recognitions, the device which is supported, which is available. All informations are available at this area. So which could be used for application in case we want to have a industry level flavor in the part. We could use these things for our applications. Right. So this is about the basic level. So I would like you to please just train these things and expand this. I've just given a basic level part on this prediction and sensor interfacing. So there are a lot of other things also there. So it is up to you. If you have any queries, you can please ask me on this section. Any questions if you have, you may please ask me.
Participants, if you have any queries, please ask.
Sir, thank you so much for the presentation.
Thank you, sir. Yes, sir.
I have a query.
Yes, sir, please.
How to decide whether we go for edge computing or cloud computing while designing an embedded system?
Sir, cloud computing, the major drawback which we have is the costs. For example, if I want to use Gmail, the same Gmail for the company which I want, I need to almost spend around 2,500 every month for me, plus all my employees. So same multiplication if I do for the number of datas, it is going to be exponential. Similarly, one more important cloud platform which is there is AWS. So even just for logging in, or even if you want to use it for a student level project, you need to pay at least $1 for it. So approximately you have to spend 100 rupees just for logging it and seeing what is there. And when we increase the data to be pushed, the cost is also going to be very high. And that's the reason when we would prefer that to happening at the edge or the device itself, wherein we can only push the data which is required, or remotely what is required, we are going to only monitor that. So that is the thing where we want to have this edge AI, or the prediction is going to happen at the device itself. Plus, what happens in the cloud, the prediction, all these things are also cost separately. For example, MATLAB have their two own tool or cloud like things be. So they have their own prediction thing done in the cloud itself. But it's also cost is going to be very high. Might be if your college is having a licensed version of MATLAB, you can use it to some extent. But still, it's going to cost us a lot. And also data storage, we can't have it up for a longer duration also. So when we want to have a prediction for a longer duration, the cost of maintaining it is also going to happen. So that's the reason we generally go with the AGI. When we want the data, only few data to be pushed. We don't want to lower the cloud, or plus the other important part is latency, which means I have to spend money for my data to push. For example, in India, we don't have that cap of data transfer as of now, because, for example, even if you take a mobile phone, you have a cap of almost 2 GB. After 2 GB, we are to need to recharge it, right? We need to recharge more. So data transfer is a major challenge. So whenever you don't want to data transfer, always you go for HAA. I hope I have cleared your notes, sir.
Yes, sir. Yes, sir. I understood the concepts. Another query, sir.
Yes, sir.
Is there any free simulator for ARM-based controllers?
Sir, actually, this OP, there are almost couple of things I'll just like to show that. This is not only for thing. You have this STM board here. This is based on ARM Cortex. This you can use even in Arduino programming. You can use that. This is the same thing running in Arduino programming. You can even use the HAL programming or C programming, embedded C programming in this, and you can simulate this. This is one with those things as a simulator, sir. But they have restriction of number of devices, and similarly, Raspberry Pi Pico is available here. It's again ARM-based versions are also there. So wherein you can do Python, MicroPython, programming in their coding and other things also, C also. So these are the things which we could use. And ESP is actually a ARM Cortex based processor. So you can even use that as a part. So these are the things which are available in that. So this is actually a tool. But what happens is we have some restriction of compiling speed and compiling time. So if you don't want, you need to pay every month or annual billing will be there. That is up to you to use it. If you want to be as a if you want compiling everything to happen faster, you need to pay money. Otherwise, if you want to have the limited simulation and Wi-Fi is virtual here, so we can't use our own Wi-Fi here. So we can even simulate a normal IoT project in this. So this is one of the free versions which we could use, which you can say
Okay.
see as a simulation, sir.
Okay, sir. Thank you. Thank you so much, sir.
Any other questions?
Any other queries?
So in case if you have any queries in the future, I'll be always happy to answer it. So that's my email ID. So I'll also share that in the chat box and my contact number there.
Okay, thank you, sir. Thank you so much for your presentation on smart sensor and embedded system for real-time monitoring. Your expertise and clear examples made the topic accessible and highly engaging for everyone. Okay, thank you, sir.
Thank you. Thank you.
And thank you. Participants, please switch on your camera to take a shot. Thank you for feedback link posted in chat box. Once fill the form, then can leave. Okay, thank you.
Thank you. Thank you.